Assalamualaikum and hi everyone. In this session, we are going to learn the final chapter of machine element design, which is brakes and clutches. I divided this chapter into two parts. The first part is brakes and the second part is clutches. Alright, in this video, we are going to learn about brakes. This is the lesson contents. This lesson covers introduction, terminology, classification and designation of brakes and clutches, types of brakes, and self-locking, self-energizing, and self-deenergizing brakes. For lesson outcomes, at the end of the session, the students should be able to differentiate between brakes and clutches, describes the different types of brakes, identify self-locking, self-energizing, and self-deenergizing of brakes. And the last one is to calculate the actuating force and torque transmitted in the braking system. Basically, brake and clutches are essentially same device. Both are high friction devices. As you can see in the figures here are the examples of brakes and clutches. The brake absorbs the kinetic energy of moving bodies and thus control the speed, while the clutch transmits power between two shafts that must be often connected and disconnected. Both have two or more surfaces pressed together with a normal force to produce a friction torque. Another difference between brake and clutch is the origin position. The origin position of the brake is disengaged until we depress the brake pedal, while the clutch is engaged. If we depress the clutch pedal, then the clutch will be disengaged. Performance analysis of brakes and clutches involve the determination of actuating force, torque transmitted, energy absorption, and temperature rise. The temperature rise is related to energy absorbed in the form of friction heat during braking or clutching. In our content, we will investigate on the first two performance analysis only, which are the actuating force and torque transmitted. The torque transmitted associated with the actuating force, coefficient of friction, and geometry of the device. The changes of these three parameters will change the amount of torque transmitted. Then we move on material selection of brakes and clutches. The brakes and clutches consist of two main parts, which are drums or discs and linings. Drums are made of cast iron, while linings are made of molded, woven, sintered, or solid materials. Asbestos has been used before to make linings, but is now banned due to health hazard issue. The friction materials used must be high coefficient of friction, resistance to wear, and heat and thermal fatigue resistance. Next, a brake accomplishes its function is by applying friction resistance between a moving member like drum or disc and a stationary member like band or shoe. One thing that all braking systems have in common is the presence or interaction of one moving component, usually rotating, of an axle, and a fixed component attached to the vehicle chassis. As you can see in the left figures here, this is the example of differential band brake. The band is originally disengaged during the drum rotates. Then, after applying the actuating force to the lever, the band will contact to the rotating drum and push the drum to slow down or stop. Same as the right figure, this is the example of internal long shoe drum brake. After depressing the lever, the shoe will push the drum to stop from rotates. Next, we move on types of brakes. There are two types of brakes are being used in industries. The first is drum brake and the second is disc brake. In our lesson, we just focusing on the drum brake only. So drum brake can be divided into two, which are band brake and shoe brake. These figures show the example of band brake, shoe brake, and disc brake. For band brake, there are two types of band brake, which are simple band brake and differential band brake. The difference is the differential band brake has a fixed lever that connect to the pivot point. There are three forces exist in band brakes. The first is actuating force, which acting on the main lever. The second is tight side tension, and the third is slack side tension. Then two important performance analyses that will be looked at in band brakes are the actuating force and the transmitted torque. Next, we move on simple band brake. Band brake is the simplest braking system. It is widely used in power excavators and hoisting. This is an example of bicycle band brake. The band is made of steel and lined with a woven friction material for flexibility. The braking system is secured by tightening the band wrapped around the drum. Refer to this figure here. The drum rotates clockwise. After depressing the lever or FA is applied, the friction force acting on the band increase the tight side tension and decrease the slack side tension. Next, the torque capacity of this brake is given by the shown equation. And the actuating force is obtained by considering free body diagram of the lever. We draw the free body diagram of the lever, then apply the static equilibrium equation, summation of moments equal to 0. Then we get the FA as shown here. A is the perpendicular distance from FA to the pivot A, and C is the perpendicular distance from F2 to the pivot A. The brake is actuated by the application of actuating force at the free end of the lever. Smaller FA is needed for operation when F1 is connected to the fixed support and F2 attached to the lever. However, if the drum rotates in opposite direction, greater FA is needed for operation because F1 is attached to the lever and F2 is connected to the fixed support. The expression of F1 and F2 is similar to flexible belt, except the centrifugal force does not exist. Let's recall the equation of flexible belt. By cancelling out the FC, then we get the equation for band brake. And the tight side tension, F1, equals to WRP max, where W is the width of the band, R is the radius of the drum, and P max is the maximum pressure. Both of these equations can be used for simple band brake and differential band brake as well. Next, we move on differential band brake. This brake is similar to simple band brake with an exception that the tight side tension helps the actuating force. This can be seen by additional fixed lever that connect the band away from the pivot point. This type of brake is called self-energized brake, since the friction force assists in applying the band. In other words, self-energized brake occurs when the moment of friction force and the moment of actuating force are in the same rotation. As you can see in the figure, the moment of actuating force rotates clockwise, and the moment of friction force also rotates in clockwise rotation. To know the rotation of friction force, we just follow the rotation of the drum. But both of the moments, which are the moment of actuating force and the moment of friction force, must rotate around the pivot point. The actuating force is calculated from the free body diagram of the lever. First, we draw the free body diagram, then apply static equilibrium equation to find the Fa. Then we get Fa as can be seen here. A, S, and C are the perpendicular distance from the respective forces to the pivot point A. Then to find the torque, we just use the same equation as simple band brake just now, which is T equals to F1 minus F2 times R. Self-locking brake occurs when SF1 greater than CF2. At this time, Fa is less than 0. When a brake is designed to be self-locking for one direction of rotation, it can be free to rotate in the opposite direction. Then it can be employed when rotation is in one direction only. Next, we move on shoe brakes. There are two types of shoe brakes, which are short shoe drum brake and long shoe drum brake. The difference of these brakes is the angle of contact. The angle of contact will determine whether the brake is short or long shoe drum brake. In these brakes, there are three forces exist. The first is actuating force Fa. This force comes from the human effort, where we apply the force. The second is normal force Fn. This force acts normal to the shoe. And the third is friction force FFN, which acts tangent to the shoe. And there are two performance analyses that will be looked at, which are the actuating force and the transmitted torque. We move on short shoe drum brake. This brake consists of a short shoe pressed on the revolving drum by a lever. The angle of contact is less than 45 degrees. Pressure distribution at the contact area, which is between shoe and drum, is assumed to be uniform. Hence, the resultant normal force and friction force act at the center of contact. The normal force of the shoe is derived from the equation of force equals to pressure times area. Then we get the normal force equation as can be seen here, where Pmax is the maximum pressure between drum and shoe, R is the radius of drum, phi is the angle of contact, and W is the width of the shoe. Next, the torque capacity of the brake is T equals to FFN times R. And the actuating force is determined by taking lever as the free body and apply static equilibrium equation, summation of moments at A equal to 0. Then we get the equation of Fa. A, B, and C is the perpendicular distance from respective forces to the pivot point A. Next, self-energized brakes occurs when the moment of friction force assists in applying the shoe to the drum. In other words, self-energized brake occurs when the moment of friction force and the moment of actuating force are in the same rotation. As you can see in the figure here, the moment of Fa and FFN rotate in the same direction, which is in clockwise rotation. The brake is self-locking when B less than or equal to Fc. As you can see here, when B less than or equals to Fc, then Fa becomes 0 or negative. So we can say that self-locking occurs when Fa less than or equals to 0. The self-energizing feature is useful, but the self-locking effect is generally undesirable. Then if the drum rotation is reversed, which is in clockwise rotation, the sign Fc becomes negative because the friction force acts in opposite direction. Thus, the brake is self-de-energized. Or in other words, we can say that self-de-energized brake occurs when the moment of friction force and the moment of actuating force are in opposite rotation. Refer to this figure. The moment of FA and FFN are acting in opposite direction, where the moment of FA is in clockwise and the moment of FFN is in counterclockwise. And also, if the pivot point is located on the other side of line of action of FFN, the friction force tends to unseat the shoe, hence the brake is self-de-energized. This is because the moment of friction force and the moment of actuating force are in opposite rotation. Next, we move on long shoe drum brake. The angle of contact of long shoe drum brake is greater or equals to 45 degrees. And most of the shoe brakes are using long shoe drum brake because most of the shoe brakes have greater than 90 degrees contact angle. The assumption is the pressure varies directly with the distance from the shoe pivot point. Hence, the maximum pressure is measured at the point farthest away from the pivot point. There are 4 measurements that you have to measure in long shoe drum brake. The first is C, where it is measured from the pivot point to the center of drum. The second is phi or contact angle, given as angle YOZ. The third is theta 1, given as angle AOY. And the last one is theta 2, given as angle AOZ. These angles are normally obtained from the trigonometry concept. Then theta 2 equals to theta 1 plus phi. Remember that we have to use the same units for theta and phi at this time. For easier calculation, we just use in degree first. The value of theta 2 is important to determine the value of maximum sine theta. If theta 2 greater than 90 degrees, then use 1 as the value of sine theta m. However, if theta 2 is less than or equals to 90 degrees, then sine theta m will be equal to sine theta 2. This sine theta m will be used to calculate the moment of normal force and the moment of friction force. Remember that at this time we have to use theta in degree and phi in radian. The actuating force is determined by taking lever as the free body and apply the static equilibrium equation. Then we get Fa as shown here. Then torque capacity of the brake is calculated using this formula. Next, we must be confused which formula will be used to calculate the Fa. So the upper sign or minus is used when the brake is self-energized brake, and the lower sign or plus is used when the brake is self-de-energized brake. So first we must identify which type of brake is used. For example, this figure is self-de-energized brake because the moment of Fa and FFN are acting in opposite direction around the pivot point A. Then we have to use the plus sign to calculate Fa. It can be self-energized brake if the moment of Fa and FFN are acting in the same direction around the pivot point A. The brake will be self-locking brake if Fa is less than or equals to 0. This condition will happen if the moment of friction force is greater or equals to the moment of normal force. Now we have reached the end of our lesson. Let's recap what we have learned just now. First, we learned on introduction of brakes and clutches. The second is types of brakes, simple and differential band brake, short shoe and long shoe drum brake. From there, we may calculate the actuating force and the transmitted torque in the braking system. And the last one is we learn about self-locking. self-energizing, and self-deenergizing brake. So that's all for this session. Thank you.